Hello, and welcome to the Big Bang Kilonova Hypothesis podcast. I'm Stuart McLean. I am both your host and the progenitor of said hypothesis. And today's episode, I want to talk about the CMB dipole. Or more specifically, I want to specifically look at two new papers that have come out. One is called A Test of the Cosmological Principle with Quasars, and the second is its reproduction. And essentially, this is trying to test a particular interpretation of what is called the CMB dipole. The CMB dipole CMB stands for cosmic microwave background radiation. But the dipole map, which is this one, is you need to talk about multipole expansion. So, in fact, I've got the words here. Now, in order to talk about the various resultant maps of the microwave sky, we have to talk about multipole expansion. In order to create a map of the entire heavenly sphere, satellite missions like COBE, WMAP, and Planck are designed to sample the photons coming from the now microwave sky from every single direction. Effectively, the flight path of the satellite is designed to rotate in such a manner that over the course of the mission, its center ends up being pointed in every heavenly direction. For each photon sampled, there is a corresponding measurement recording the direction from which that photon came. Thus, for each photon of the microwave sky sampled, there is a corresponding set of spherical polar coordinates related to the region of the sky from which it came. A multipole expansion is a function written as a mathematical series, most commonly as a sum of spherical harmonics, where that function is dependent on angles. It is employed as an analytical tool where the collected data can be mapped onto a sphere, such as the case for mapping the cosmic microwave background radiation. The maps produced from multipole expansion are dependent upon the number of sums in a given series. The greater the number of the sums used in expressing the function, the higher the resultant resolution of the map, as finer angular features are revealed. However, the higher the resolution of the resultant map, the greater the number of data samples required. This is evident in the number of samples collected between the subsequent missions of COBE, WMAP, and Planck, which in turn produce higher resolution maps. The resolution of the multipole maps is expressed in terms of progressively finer angular features or moments. The first term in the summation is called the monopole moment. The second term is called the dipole moment. The third, the quadrupole moment. The fourth, the octupole moment, and so on. A multipole moment usually involves powers and is expressed in terms of 2 to the n, where n is a positive integer. Or another way of putting it is with Fourier analysis. Spherical harmonics and multipole expansion are effectively performing a Fourier analysis on a sphere, as opposed to, say, a one-dimensional Fourier analysis or a two-dimensional Fourier analysis. So say you're doing image analysis and you want to find all the frequencies of the colors within a given picture. So you do a 2D Fourier analysis to get all the spectral components, the red, the green, the blue, from an image. And essentially, the Fourier analysis is used for taking data in the spatial domain or temporal domain and finding the frequencies within within that given data, be it an audio file, an image, or in this case, it's the microwave sky. But because the microwave sky is mapped to a sphere, to the heavenly sphere, which is essentially the night sky that we see, there it is finding the frequencies of the essentially is you're looking for the frequencies of standing waves within the plasma or within the temperature fluctuation. The temperature fluctuations way the way if I remember it goes right. So you've got so the early universe is hot ball of homogeneous and isotropic plasma, and now and as regions with greater density within them have a greater gravitational attraction, it pulls stuff in towards it, and as the region becomes denser and denser, it becomes hotter and hotter. Whereas a region where stuff is having matter pulled away from it becomes colder and colder as it becomes less matter within that Pacific area. So what we're trying to do in sampling the microwave sky and creating these temperature maps, which then correlate to density of the early universe, i.e. most of the matter's here, as opposed to being most of the matter here. So in the first mission, which was the Kobe mission, they discovered this the CMB dipole with a fluctuation of 1 in 1,000. Now this is in complete comparison to what they find the temperature fluctuation of the quadrupole maps or the octuple maps or any other subsequent map is that they find that the temperature fluctuation is 1 in 100,000. But the dipole map is 1 in 1,000 variation. So there are so I present my hypothesis, and then there is the Lambda CDM models explanation for this. It is also the explanation, Lambda CDM models explanation for why we're seeing the local group of galaxies moving around this local void, this massive local void. So I'll start with the Lambda CDM models explanation, and then I'll present my explanation as an alternative, and the test of it really comes down to these two particular papers. And I am so over the moon at the moment. I am. This is, of course, if you saw my podcast from the other day, I only saw these two papers after giving an explanation for God in terms of Darwinian, when phrased in terms of astrobiology and Darwinian evolution. Where did God originate from? And in turn, while doing that, straight after that, I see these two papers here. So, as a note, the reason these two particular papers came came to my attention was because I came across I saw Sabine Hoffenfelder's uh, video yesterday where she talks about the cosmological dipole anomaly confirmed, which which essentially means these are part of the microwave sky. So let me present the Lambda CDM model, and then I'm going to present the Big Bang Kilonova Hypothesis model. In order to talk about Lambda CDM's interpretation, it comes down to this idea of dark flow, where dark flow is a theoretical non-random component of the peculiar velocity of galaxy clusters. And essentially, it's summed up in this one picture here. This here is our Milky Way galaxy. We've got the Andromeda galaxy right next to it. And then we've got all the other galaxies surrounding us that make up the local group. And it's showing the velocity and the direction of travel of all the galaxies within the local group. And they're all going in the same general direction. And that same general direction is that on the other side of the Milky Way galaxy from us is a massive void. It's called the local supervoid. Is it a local supervoid or just a local void? So, the local void is a vast empty region of space lying adjacent to the local group. Discovered by Brent Tully and Rick Fisher in 1987, the local void is now known to be composed of 3 separate sectors, separated by bridges of wispy filaments. Let's have a look at that one. The precise extent of the void is unknown, but it is at least 45 megaparsecs, 150 million light years across. Boretes is 330 million light years. Eridanus is about 500 to 1,000 or a billion light years across. So effectively, we have this massive region of nothingness on the other side of the Milky Way galaxy, and all the galaxies are flowing in one particular direction around it. So that's what's being observed, and the explanation for it, is this thing called dark flow. And one postulate says that we see ourselves moving towards the direction of the Leo shape, Leo and Centaurus. So this region generally in here, that's where we're seeing this general flow of galaxies. So all these arrows, so that particularly point going in that direction, from our point of view on Earth, we're seeing ourselves moving in. We see the Milky Way galaxy moving in the direction of the constellation of Leo. So, yeah. So I'm just going back to one hypothesis proposes that here in the shape here, there is a massive concentration of, there's a massive supercluster of galaxies that is either invisible to us because you have the Milky Way galaxy standing between us and that line of vision. So look, so being on one side of the Milky Way galaxy, we try to look across it. We're having to view across the expanse of the Milky Way galaxy before we even see out towards this supercluster in the that's in the direction of the constellation of Shapley, or this is supercluster of galaxies that is beyond the observable horizon. I think and there's another one which proposes both of them. There is there's a supercluster of galaxies towards the Shapley cluster, and then there's an even bigger concentration beyond the observable horizon, beyond our observable horizon, and the gravitational effect of that is pulling us and everything else in the local group towards it, and so effectively this big concentration of galaxies that lies in the shape lies in the Shapley or what's called as the Shapley supercluster, and then there's another supercluster beyond that. The gravitate we may not be able to see them, but the gravitational effect exerted upon us, upon the Milky Way galaxy, upon the Andromeda galaxy, the local group, is to pull us in that general direction, and that pull is called dark flow. It's like anything else in the cosmology. Just add the word dark to it. Can't explain it. It's or there is no consistent one explanation, even though it constantly violates the precious cosmological principle that the universe is homogeneous and isotropic. So, from the point of view of us measuring the microwave background sky in our own in our own solar system, traveling through the Milky Way galaxy, and the Milky Way galaxy, along with a local group, has this tendency to move towards the constellation of Leo and away from the constellation of Aquarius. I've got some nice graphics in regards to that. So here I show the movement of Earth and our solar system with respect to how we see it relative to the constellations of to the constellation of Leo and to the constellation of Aquarius. So that's, or to put it another way, the Milky Way is traveling in a direction which to us looks like we're moving in a direction towards Leo, and we're receding, we're moving away from Aquarius. And so the explanation goes that light from the microwave sky is increasingly being blue shifted. So the line is moving toward the blue end of the spectrum, and the light wave is becoming bluer and bluer. It's becoming so because we're moving towards the microwave sky. Effectively, it blue shifts the light that we see coming from the microwave sky because we're moving towards it, and vice versa. I think that the light from the microwave end of the spectrum, or the microwave sky coming from the direction of Aquarius, is being redshifted because the Earth is moving away from it's moving away uh from the light from the microwave sky. So light from the microwave sky from the direction of Aquarius is increasingly being redshifted because as our solar system is moving away from it, it implies that light is this doppler shift effect of the light is seen such that we see it more in the red end of the spectrum. So being in the red end of the spectrum, it is colder. Being in the blue end of the spectrum, whereas blue shifted is hotter. So it can create a bit of a faux pas. This is temperature fluctuation. So over here, the light is being red shifted, and so it's colder. Because it's colder, it's blue. Because it's over light coming from here is increasingly blue shifted. Because it's blue, it has more energy, and thus it has a higher temperature. So that, in a nutshell, is the Lambda CDM model's explanation. On top of this, we need to add how do voids form according to the Lambda CDM model? How do these volumes of dark energy around of which the local group is one, but it talks about wispy filaments within it. So there is so I'm a, so in accounting for wispy filaments, I would point your attention to firstly here the cosmological principle, followed by the void, where I'll present these arguments later on here. I explain the wispy filaments there that we see in the local void being the vast region of empty space that lies adjacent to the local group discovered by Brent Tully and Rick Fisher in 1987. So this picture here is coming from Brent Tully's work, where he maps out the cosmology of the local void, in which he produces this map showing the flow of galaxies around this volume of dark energy. But dark energy is considered to be like it's believed to coalesce like soap bubbles. That's a soap bubble model where if you blow some soap bubbles, then you can merge them together and grow them and grow them and grow them. And as soap bubbles merge into one another, the bubble grows larger and larger and larger until it becomes one bubble. Or you might have multiple bubbles in the volume of one bubble, and so that's a general explanation of how these filaments are formed. Galaxies are pushed onto the filaments as voids form. I think I've got another one around showing another simulation. Hopefully can try and find it here. So here's another here's what I was looking for. This particular image here. Let's expand upon, and it shows the evolution of the model. So we start off with a description of the universe being a homogeneous isotropic plasma, where everything looks the same, but it's got these. But inflation theory says that due to quantum fluctuations, there are ripples, and the and it cause some regions to develop into or the explanation for how a galaxy forms is so utterly pathetic, in my opinion, that it is an absolute total joke. Of how spiral galaxies form. For my explanation of how spiral galaxies form, I point to my anatomy of a kilonova, where I also answer the question, why is the universe homogeneous and isotropic? Sorry, not to be so insulting, but we start with a homogeneous isotropic, or mostly, where galaxies are formed, and the distribution of galaxies is more or less homogeneous and isotropic. There's no real regions or voids. And if we just look at the cosmological principle, the reason why the model starts in this particular state, actually that got some nice graphics here showing it. But essentially it reflects the cosmological principle, the notion that spatial distribution of matter in the universe is homogeneous and isotropic when viewed on a large enough scale. So they describe the Big Bang as, or 200,000 years after the Big Bang, as the universe is essentially one large ball of hot, homogeneous, and isotropic plasma, and some regions have got higher concentration, and those regions are collapsing down to form spiral galaxies, and in some regions they should have large gravitational collapse in order to create the supermassive black holes that we see. Well, actually, there's no real explanation for supermassive black holes by the Lambda CDM model. For my explanation of where supermassive black holes are coming from, talked about it yesterday on my previous podcast, and it's really in my this piece of work is where I'm really saying where supermassive black holes are coming from. But side aside, yes, cosmology in many areas is very lacking, and I say that because I'm presenting my own explanations as opposed to compared to what the rest of the theoretical cosmology has managed to say. But yes, that is why we have a homogeneous mixture of galaxies. But inflation theory says that like soup bubbles coalescing together that grow and grow, regions of dark energy are attracted to each other as regions of normal matter are attracted have gravitational attraction towards one another. So anything all the galaxies are made out. They have gravitational attraction to each other, versus dark energy, which which is responsible for the expansion of the universe, is pushing everything away as it is attracted to it itself. But we, being made of not baryonic matter, ordinary matter of atoms, are repulsed away from it, and we see this repulsion away from it in this picture. This is what is actually being observed, and so is what is trying to be explained. And so it uses a soap bubble model, of which this is one of them, to show how galaxy filaments come together. But the implication of that is that around, if galaxies are being pushed onto filaments, then they should generally being pushed away. They should be moving perpendicularly away from the local void. So rather than, say, flowing around it, rather than flowing around it as we actually observe, we have to have this new explanation attached onto why we're seeing this, in the concept of dark flow, which is this non-random component. And all of this, so in seeing at the local level, and this curious alignment that we have to the equinox, the direction of the equinox is the dipole movement, north and south elliptic. So this is the line of the ecliptic poles. Basically, Earth has a very, very, very unusual alignment to this feature, which is a violation of the cosmological principle. And that particular alignment. So because of this alignment, people thought that it was due to the relativistic motion of our galaxy. So light coming from Aquarius, microwave skylight, is being blueshifted. No, it's being redshifted here, and light from here is increasingly being blueshifted. Thus leading to us seeing this on the microwave sky. So that's how all these link together, according to the Lambda CDM model. Okay, so how do I account for all this? And for that, okay, this is essentially what I've called computational model 1.0. Effectively, it is using the physics engine within the software package Blender. I take a single magnetic field, and I animate a bunch of particles, creating this fine jet formation, this concentric series jet formation, as an effect of a single magnetic field. And in it, we've got where the original particles are originally coming from, and then a space that opens up in between. So the space that opens up in between is my explanation of how the Eridanus supervoid formed at the time of the cosmic microwave background sky. This is then this is in opposition to Lambda CDM model, which says there shouldn't be any super void there, but yet it keeps appearing in the microwave sky, nullifying their explanation of that. But the cosmologists are arguing over, well, is it statistically significant or is it not? Well, it's 10 times colder than the rest of the region. So just so you know, Excel for my explanation of CMB cold spot, i.e. this point here, the Eridanus supervoid, you see here and here, versus the Lambda CDM simulation of how voids form. So that particular animation we were looking at earlier, that's coming from this particular paper here. Vast cosmic voids merge like soap bubbles. So just to add to it, but I essentially presented the argument I'm already presenting here for you, but this space that opens up between the source where everything is, and then we have everything. Notice all the particles are moving in the same direction. It's all being. So we start the model again. Everything gets blasted off and then moves in the same general direction of travel. So if we consider um, the motion of a particle, of one particle with respect to another, this animation shows that a little bit better. So we're moving with the actual jet itself to see how it actually forms into a series of concentric layers. But we stop here. Everything with respect to everything else is moving in the same general direction, and they're all moving as one homogeneous group. So effectively, the inflation of the inflation of the universe. So I'll bring up this. So I say our universe inflates. It's a entrapped manifold of space-time that inflates inside the larger scale verse that I've come to call the superverse. So everything is flowing in the same general direction. So rather than particles and what I used in the previous animation, I'm using small scale galaxies. And if you look, and I've got animations of. So if we were inside the balloon, all the galaxies flying off together, and we fly along with those galaxies, and those galaxies all moving at the same general all in the same general direction, with all the same general speed. Dark energy in my model is that mass energy density of the. So I'll just stop it at the beginning here. So I use water to kind of like illustrate the flow of our universe. Vice versa, I have an object of the superverse, namely a star of the superverse, which is spherical in shape. Fractal geometry is the cosmological principle, and self-similar patterns repeat irrespective of scale. and there is a large void measuring 330 million light years in the Boreas constellation. And then, as we've seen, there's the local void, which measures 150 million light years in diameter. So we have these objects that are objects of the superverse, just as our universe is an object of the superverse. But they're two separate objects. They're not one and the same. But here, our universe is flowing in the direction of this other object of the superverse, a star of the superverse. And as it flows towards it, it flows around it. So that's how, and so from our perspectives, being inside our universe, we see the formation of these voids comes into being by our universe co-inhabiting the same volume of space within the superverse as this particular object, i.e. this star of the superverse. Of course, it may or may not be a star. It could be a planet. It could be an asteroid. You just don't know what the scale is. I say it's a star because 330 million light years in diameter, or sphere. The Boreas void is sphere. It's spherical in shape, and being a star of the superverse, it has rotation, and this rotation can draw matter into it, and so there are 60 galaxies within the Boreas void that are strung out along a particular filament, and this runs through its central axis of. So I'm saying this filament is the central axis of rotation of the star, and our universe has been pulled into it. So that creates that particular filament. So in this way, this is how I am distinguishing myself from the Lambda CDM model in trying to test my hypothesis, because I'm expecting the flow of galaxies around the Boreas to be in such a manner that we see everything coming from one general direction, and the universe flows around it. But in the case of the local group, we do see it flowing around it. That's how I account for it. Plus, it is also how though until actually specifically looking at these two very specific papers here, I haven't really given much thought to the CMB dipole. Okay, or I wasn't sure. There is good reason to believe, or the vast majority of cosmologists believe, that the CMB dipole, and we'll get back up again here. Yeah. The CMB dipole, actually, I given thought to the CMB dipole in terms of Lion Shamir's work of galaxy asymmetry. But one of the things that I wasn't previously aware of was this particular magnitude. So if we just read the first paragraph of this particular paper, the standard Friedmann-Lemaître-Robson-Walker FLWR cosmology is based on the cosmological principle which posits that the universe is homogeneous and isotropic on large scales. This assumption is supported by the smoothness of the CMB, which has temperature fluctuations of only 1 part in 100,000 on small angular scales. These higher multipoles of the CMB angular power spectrum are attributed to Gaussian density fluctuations created in the early universe with a nearly scale invariant spectrum, which have grown through gravitational instability to create the large-scale structure in the present universe. The dipole anisotropy of the CMB is, however, much larger, being about 1 part in 1,000 as observed in the heliocentric rest frame. This is interpreted as due to our motion with respect to the rest frame in which the CMB is isotropic and thus called the kinematic dipole. So this is a Doppler explanation that we were talking about earlier. According to the most recent measurements, the inferred velocity is 369.82 plus or minus 0.11 kilometers per second towards L. So we're looking at some particular coordinates. This motion is usually attributed to the gravitational effect of the inhomogeneous distribution of matter on local scales, originally dubbed the Great Attractor. The Great Attractor being that shapely supercluster, or the one that's beyond the line, beyond our observable height, which is even larger than normal. I think, yeah, the normal cluster. That's what that is saying. It's these large superclusters and the local group's attraction towards that cluster being dubbed the Great Attractor. So if I was to take Occam's razor, the simplest explanation usually tends to be the correct one. Well, my explanation is, as I say, our universe is essentially expanding in one given direction. Everything's moving in the same general direction. Objects exist in the way of the expansion of our universe. These objects are objects that belong to the superverse into which our universe is expanding. So our universe is mostly flat, as measured by the CMB, because the space into which it is expanding, the space of the superverse as our universe is expanding into, is itself mostly flat. But it's not flat everywhere, because you have objects of the superverse that exist. One of those objects can go hypernova and give birth to a pair of new universes, or they can collapse into neutron stars of the superverse. Two of those neutron stars of the superverse orbit around each other, and you have the Big Bang Kilonova Hypothesis, which pushes everything in the same, produces a new entrapped surface of spacetime that is expanding out into the volume of its void. But in its path, there is a star. There is a foreign object of the superverse, and our universe flows around it as it all moves in the same general direction. And again, I use that same explanation to explain the formation of the Eridanus supervoid at the time of the CMB. See, according to the Landis CDM model, So according to the Lambda CDM model, where cosmic voids merge like soup bubbles, that takes time. And one of the great controversies about the Borealis supervoid was there has not been enough time for dark energy to coalesce in such a manner that into such a large enough volume that that for this to the amount of time required for this to actually happen according to the models is greater than the time span of the Big Bang. Of course, then some other people produced some other models of the parameters tweaked and said, actually, no, we can create the Borealis void in the time of it is taken. So I think that's probably around. You have to put it less than 12 billion. I'm just trying to account for how far the Borealis void is from us thing. I think it's 75 million light years. So, or talking about millions of light years. So yeah, 13.8. Say 13.7 billion years is the length of is enough time for the Borealis void to have formed via this particular explanation. If voids take time to form, how does the Eridana supervoid, which exists at the time of the last scattering of the CMB, cosmic microwave background radiation, how does that? What's Lambda CDM model got to say about that? Statistical anomaly. Just says, but in turn here, what has the Lambda CDM model got to say about this being a part of the cosmic microwave background sky? And this is the case that I'm putting here. This dipole that we see, which matches up with an observable cosmological parameter being the asymmetry of the asymmetry in the spinward direction of spiral galaxies. So essentially, spiral galaxy can have a anti-clockwise spin, or it can have a clockwise spin. So that's what these particular. So I use these use the symbology here to kind of help me illustrate that very specific notion between clockwise spin and anti-clockwise spin. And we see galaxies, we see an anisotropic universe, because up here and down here we're seeing this asymmetry in the spinward direction of galaxies, and we're seeing the same thing when it comes to the quadrupole map. And so this is a cosmological. And so the important thing about Lionel Shamir's work to me was it gave me a cosmological something that measure directly observing the spinward direction of spiral galaxies is something that you see through the telescope, as opposed to measuring the microwave background sky and its temperature. But this is a observable cosmological feature that we're seeing also align up with the quadrupole map of the temperature fluctuations of the very early universe. But Lionel Shamir's work is just one, has got to be reproduced, and it's very easy to argue against it. These papers, however, they are a lot harder to argue against. One, because we've got reproduction. So if we look down in towards these papers, what they're essentially doing is looking at quasar groups. Yeah, I think we probably really want. So in the next part, we'll actually start looking at these very specific papers. But the fact of the matter is that this graph here is showing what a relativistic, a kinematic interpretation of the CMB dipole. So that's that doppler shift effect I was talking about. So if that model is correct, we would expect this, but from the quasar data, we're seeing it actually being part and parcel of the cosmic microwave background radiation, meaning this dipole is quite certainly not due to Doppler shift, but due to the entire movement of the galaxy as a whole. That's why this is so important for me, because this is more or less handing me victory in a nutshell, based on the arguments I presented. Occam's razor, which is the simplest explanation. Well, with the Lambda CDM model, dark flow, great attractor, we'll just add in dark energy. It just adds and adds and adds. It's not thought out. It's something that's been reached by consensus, not. And so it makes me look at the cosmological community and go like, oh my god, what you guys even think? But that's the thing. That's the thing about this. See, I mean, until you actually think about it, you're not getting it. I thought about it, and now I own key pieces of real estate, namely the Google search engine. I'm on top, but yeah. So like I say, in the next section, when I carry on, let's go through these very specific papers now that I have presented the Lambda CDM models explanation versus the Big Bang Kilonova Hypothesis explanation. Oh my. Oh wow. Oh, hello. And yeah, we're back. So I was going to talk about these specific papers here and go through them. A test of the cosmological principle with quasars. Oh, just as a side note, uh, between recorded the last section at around about 3 o'clock, and now it's about 6 o'clock, and I've just received my new book. Oh, I'm so excited for this book. Let me show you. I've been waiting for this since November. It's a very, very rare book. The Primeval Atom by Canon George Lemaitre. I'm surprised it's such a rare book. I only found one bookseller in the world that actually was doing reproductions or reprintings of this specific book. George Lemaitre is the father of the Big Bang, and as he proposed, he's proposing the idea of the primeval atom. let's look at, so just to put this into context, the ideas expressed in this book are what gave rise to the FLWR FLWR metric, which is the cosmological solution that the Landis CDM model uses. It is a cosmological solution of general relativity. And many of the essays in this book are the development of that particular metric. It's also the development of the actual Big Bang theory itself, where they discovered that the universe is actually expanding. And it's coming from a time where, well, in the 1920s, the name of galaxies was island universes. The size of the universe we thought was confined to the Milky Way galaxy, but we found that we live in a universe that is bigger than the Milky Way galaxy. In fact, it's a universe full of trillions and trillions of galaxies, and those are the ones that we can see to the observable horizon. So, at some point, in the next couple of podcasts, I'm going to be reading through the various essays in this book, and we can go through them together and have a look at the original source material of George Lemaitre. But it's his idea of the primeval atom that I'm more or less resurrecting. I'm more or less, because effectively, the binary merger of two neutron stars is the binary merger of two primeval atoms. And because effectively a neutron star can be described as a massive atomic nucleus. So I'm resurrecting George Lemaitre's idea of the primeval atom, which has been ignored. It's almost so unknown that I only found one bookseller in the entire world that's actually reproducing this book. So, that puts things into context. But for this paper, let's go through it. Abstract. We studied the large-scale anisotropies. Let me just increase the resolution on this so we can read it better. We study the large-scale anisotropies of the universe by measuring the dipole in the angular distribution of a flux-limited all-sky sample of 1.36 million quasars observed by the Wide Field Infrared Survey Explorer. So that's this particular mission here. This sample is derived from the new CatWise 2020 catalogue, which contains deep photometric measurements at 3.4 and 4.6 micrometers from the cryogenic, post-cryogenic, and reactivation phases of the WISE mission. While the direction of the dipole in the quasar sky is similar to that of the cosmic microwave background, its amplitude is over twice as large as expected, rejecting the canonical, exclusively kinematic interpretation of the CMB dipole, with a p-value of 5 to the 10 to the minus 7, giving a 4.9 sigma for a normal distribution one-sided, meaning that's a level of certainty, 4.9 sigma for this particular the highest significance achieved to date in such studies. Our results are in conflict with the cosmological principle, a foundational assumption of the concordance lambda CDM model. One of the questions I really want to try and understand in this paper is, what is it exactly that they're measuring from the sample of 1.36 million quasars? What is it that they're measuring? I think it's the term. I'd say the explanation is that if I go back to here, the explanation is this is unusual. This movement of the local group is unusual, and our movement through the universe relative to the rest of it is producing this dipole result. So I think they're looking at the movement of various quasars and mapping out the direction of flow of these quasars, which way they're moving through the universe with respect to us. And the question is, it's kind of really being posed as, if you're an observer in one of these other galaxies that far away, what would they look at? What would the dipole look like to them? Would they see the CMB dipole or not? So, introduction. The standard Friedman-Lemaitre-Robertson-Walker cosmology is based on the cosmological principle, which posits that the universe is homogeneous and isotropic on large scales. Fractal geometry is a cosmological principle. This assumption is supported by the smoothness of the CMB. I think I smirk because Penrose smirks so he goes, fractal cosmology, cosmological principle. No, Penrose. Fractal geometry is a cosmological principle. This assumption is supported by the smoothness of the CMB, which has temperature fluctuations of only 1 part in 100,000 on small angular scales. These higher multiples of the CMB angular power spectrum are attributed to Gaussian density fluctuations created in the early universe with a nearly scale invariant spectrum. What exactly do they mean, scale invariant spectrum? Anything in the word scale invariant in it is always interesting. So let me reread that for you. These higher multiples of the CMB angular power spectrum are attributed to Gaussian density fluctuations created in the early universe with a nearly scale invariant spectrum, which have grown through gravitational instability to create the large-scale structure in the present universe. The dipole anisotropy of the CMB is, however, much larger, being about 1 part in 1,000, as observed in the heliocentric rest frame. So the heliocentric rest frame is our position on Earth, or from the Y, or more specifically, it's from this particular satellite, is the frame of rest that we're doing our measurements from. This is interpreted as due to our motion with respect to the rest frame in which the CMB is isotropic, and is thus called the kinematic dipole. So that was that whole explanation of our solar system moving towards the direction of Leo and away from Aquarius, creating this doppler shift. And the specific speeds of the doppler shift is, according to the most recent measurements, the inferred velocity is 369.82 plus or minus 0.11 kilometers per second towards L, B equal, so we've got some coordinates in the sky. So that's sort of really in the direction of in the constellation towards Leo, towards the Great Attractor. This motion is usually attributed to the gravitational effect of the inhomogeneous distribution of matter on local scales, originally dubbed the Great Attractor. Also, what we're talking about, the Great Attractor being what we think is the Shapley supercluster and the Noma supercluster. But really, I don't think there's either we can't see it or there isn't. I'd just say there isn't enough stuff in there to cause such a gravitational attraction towards it. A consistency check of the above kinematic interpretation of the CMB dipole would be to measure the concomitant effects on higher multipoles in the CMB angular power spectrum. However, even the precise measurements of these by Planck allow up to 40% of the observed dipole to be due to the effects other than the solar system's motion. So referencing previous work, so I think we probably want to have a look at these at some point. According to galaxy counts, in large-scale surveys, the universe is sensibly homogeneous when averaged over scales larger than greater than 100 megaparsecs, as indeed expected from consideration of structural formations in the concordance Landis CDM model. I just got one thing to say about that. There's been numerous cases over the last couple of years. Some I cover. One I think I particularly talk about here. Large scale. So there's like a. Yeah, here we are. Oh well. Oh, here's another one. It's a giant arc, 3.3 billion light years long, that shouldn't exist. And then there's another one that's 8 billion light years long. So they're finding these structural formations within the universe that are in complete violation to the cosmological principle that the universe should be both homogeneous and isotropic. So according to galaxy counts and large-scale surveys, the universe is sensibly homogeneous when averaged over scales larger than greater 100 megaparsecs. As I said, there are many cases of that being disproven. Void is one such case. Are large-scale arc structures across the entire universe, measuring 9 billion light years in length, is far bigger than 100 megaparsecs. Hence, the reference frame of matter at still greater distances should converge to that of the CMB, i.e., the dipole in the distribution of cosmologically distant sources induced by our motion via special relativistic aberration and doppler shift effects should align both in direction and in amplitude with the CMB dipole. Independent measurements of the distant matter dipole are therefore a crucial test of the cosmological principle and equivalently of the standard model of cosmology. Ellis and Baldwin, 1984, proposed that such a test be done using counts of radio sources. These are typically active galactic nuclei, or quasars, at moderate redshift of Z roundabout 1, so locally clustered sources at Z being less than 0.1, so relatively close, which can introduce an additional dipole in the distribution of matter, are not a significant contaminant. Consider a population of sources with a power law spectrum SV proportional to V. So this is where it's I'm trying. So this is where it gets into the analysis of how we're going to use quasars in order to test the dipole. I don't understand how exactly they're doing it. We're moving with velocity v strictly less than the speed of light with respect to the frame, being which these sources are isotropically distributed, then being tilted, we should see a dipole anisotropy of amplitude. So this is where this work is being referenced from. Yeah. So this is obviously I'm trying to understand the methodology that they use in radio. So this is you're using radio astronomy, but is looking at active galactic nuclei or quasars feeding where the supermassive black hole is feeding. If the standard interpretation of dipole anisotropy and microwave background radiation as being due to our peculiar velocity in the homogeneous isotropic universe is correct, then radio source number counts must show a similar anisotropy. Conversely, determination of a dipole anisotropy in those counts determines our velocity relative to their rest frame. This velocity must agree with that determined from the microwave background radiation anisotropy. Present limits show reasonable agreement between these velocities. Okay, I think I begin to see how so the Doppler shift and other various effects that add up to the CMB dipole. So I'll just bring up the CMB dipole so we can see it. So the Doppler shift then caused by our motion through the universe is producing this. Well, that's the idea that's being tested. And if the light from the microwave sky is being Doppler shifted, then so should the light from distant quasars also be effectively Doppler shifted, such that it matches up with the microwave sky's background radiation. So that effectively is what these particular paragraphs are about. It's about the history of starting with where did we have it? Just had to open it up just a second ago. Look away. Where was it? Oh, 1984. So starting with this particular test here, and then they've developed a series of experiments along with all the various bits of mathematical analysis that goes along with it, such that effectively, in looking at the CMB dipole and saying it's due to a Doppler shift effect, then light from from various quasar groups should also show the same Doppler shift effect in the microwave sky. And that's the question that's being essentially proposed here. And so that so there's a whole series of like particular analysis and mathematics that's developed in order to test this hypothesis. So in this letter, we report the first independent measurement of the dipole in the angular distribution of distant quasars using mid-infrared data from the Wide Field Infrared Survey Explorer, which surveys the sky at 3.4 micrometers, 4.6 micrometers, 12 micrometers, and 22 micrometers. This provides a measurement of the dipole that is independent of the radio survey-based results, as WISE is a space mission with its own unique scanning pattern, not constrained by the same observational systematics that affect ground-based surveys, such as declination limits or atmospheric effects. While WISE, along with 2MASS, has been used before to set useful constraints on the matter dipole, these studies were of relatively nearby galaxies, I saw in the local group, where contamination from local sources can be significant and has been carefully accounted for, i.e., all this, all the movement of all the galaxies in the general flow around the local void. Essentially what they're talking about. Significant. In section, so sources can be significant as carefully accounted for. In section 2, we detail the quasar sample that we use and we introduce our methodology in section 3. Our results are presented in section 4 and we discuss their significance for cosmology in section 5. So, the actual data set, quasar sample. Because of the unique power of mid-infrared photometry to pick out active galactic nuclei, WISE may be used to create reliable AGN quasar catalogs based on mid-infrared color alone. We require an AGN sample optimized for cosmological studies, so the objects should preferably be quasars. Active galactic nuclei dominated and at moderate or high red shift, with Z greater, so the ones that are not part of the local group. The sample should cover as much of the celestial sphere as possible to minimize the impact on missing or masked regions, and be as deep as possible to contain the largest number of objects and thus have the greatest statistical power. We created a custom quasar sample from the new CatWise 2020 data release, which contains sources from the combined 4-band cryo, 3-band cryo, post-cryo NeoWise, and reactivation NeoWise R data. I just want to, so looking back to here, I'm not saying like launch NeoWise. So there's also periods of the mission that has gone through where it's full scale there. The wise mission was put into hibernation first, and then brought out of hibernation. So yeah, it's referring to the different periods within the actual mission itself, within the wise mission itself. So the CatWise 2020 catalog is 95% complete down to 17.4 Mach. So it's talking about how big the catalog has become from the missions. We select all sources in the Cataract catalog with valid measurements in W1 and W2, which are the most sensitive to active galactic nuclei missions. To avoid any potential directional bias from uncorrected galactic reddening, we corrected the W1 and W2 magnitudes using the Planck collaboration dust map and the extinction coefficients from Wang and Chen. So effectively, ensuring that they're cleaning the data that has got that the color of the active galactic nucleus, it has not been good. They're cleaning it for like any dust maps and for interstellar gas that light us pass through when traveling through the Milky Way galaxy towards us, and other such factors to essentially get the right color of of the quasar itself. So essentially, the Planck collaboration, that's the Planck mission. To select quasars, we impose the color cut W1 minus W2 greater, which indicates an active galactic dominated emission followed by a power law distribution. This yields a raw sample of 141,698,603 objects. So, effectively looking for lots and lots of active galactic nuclei from everything that the WISE mission has seen. To remove poor quality photometry, near clumpy and resolved nebula, both in our galaxy, e.g. planetary nebula, and in nearby galaxies such as the Magellanic Clouds and Andromeda, we produced masks for the nebula and used masks of size 6 times 20 mag parsec, so a certain area of the sky. Isophoto radii from the 2-mass large galaxy Atlas for the Magellanic Clouds and Andromeda. So effectively masking out anything that is sort of already known about, which could affect the results, like planetary nebula, or the Andromeda galaxy, or so taking into account all the nearby objects, but we're placing a mask over them. In the WISE catalog, there are often image artifacts near bright stars caused by density suppression in their vicinity. We find that circular masks with 2 mass K band-dependent radii log equal to particular temperature effectively removes these. We removed any remaining areas of poor photometry or artifacts using masks of radius less than 2 degrees. In all, we masked 291 sky regions, not including the galactic plane. So effectively, trying to remove anything that has got a poor quality image from this collection of objects. Above a W1 magnitude of 16.4, uneven source density appears due to overlaps in the ecliptic scanning pattern of WISE, most prevalent at the ecliptic poles. We select a magnitude cut 9, so a particular cut from one section of the data set, where the lower bounds guard against potential saturation, while completeness in high source density areas in CatWise 2020, hereafter CatWise, is improved over the CatWise preliminary catalogue. We nonetheless find a drop-off in source density below galactic latitudes and a mild inverse linear trend in source density versus absolute ecliptic latitude. This trend has a slope of minus 0.51 and a 0 latitude intercept. We include this fit as a correction of weighting function. Or effectively, what's going to talk about is we remove these, leaving a final sample after masking of 1 million quasars, as shown in figure 1. So left, Molly-Well density map of our cat-wise quasar sample in galactic coordinates. So this is this. So let's have a zoom in on this. So effectively, you've got the Milky Way galaxy here, and so discounting the region here because that's where the plane of the Milky Way galaxy is. You've got larger ones like Andromeda and the Magellanic clouds. So any areas that have been masked out are areas where line of sight from Earth is seeing objects or line of sight from our solar system, because WISE is a spaceborne observational mission. So that's what the dataset is. Molly-Well density map of our cat-wise quasar sample in galactic coordinates. Right, density map smoothed using a moving average on Sterling scales, showing a dipole signal. Both maps have been corrected for the residual ecliptic latitude. So see how it's blue here, but I want to probably put these into two Molly-Wells, my Molly-Well projector, and see what they look like. But effectively, you've got a blue dipole here, a red dipole more or less sort of kind of here. And so that's what their data set's showing, as opposed to go to dipole map. Here's the dipole map. So you see these are in these regions here, but their dipole map, based on their data set of quasars, is producing dipoles over here. So if what they were expecting, given a kinematic interpretation of the dipole, or CMB dipole, meaning it's a doppler shift and other effects, is that it should be here and down here, rather than the blue bits being here and here. So I think that's what's actually being shown. Both methods have corrected for the residual ecliptic latitude bias. That's figure 1. We calculate spectral indices alpha over a sample in the W1 band by taking power law fits of the form SV. So, I could go through this paper, but let's just, because it talks about very, very specialized interpretation or analysis. So let's get to discussion. Essentially, what have they found? What are the, or maybe we want to have a look at 4 results. Our sample of 1,355,355 quasars exhibit a dipole with amplitude d equals 0.01554, pointing towards L equal. This is 27.8 degrees from the direction of the CMB dipole, and over twice as large as the expected amplitude of around 0.07 using equation 1. The amplitude and the direction are largely unaffected by varying the mass sizes for both estimators. For instance, doubling the size of the point source mass or introducing a 10-degree mask along the supergalactic plane changes the dipole amplitude by less than 5%, and the direction of the found dipole varies by 5%. So even trying to adjust the results, they're not finding it aligning up with the CMB dipole. When the expected dipole is simulated, assuming the kinematic interpretation of the CMB dipole, only 5 out of 10 to the power 7 such simulations give a simulation with an amplitude larger than the observed value and within the observed angular distance from the CMB dipole. We can therefore reject the null hypothesis, where with a p-value of 5 times 10 to the power minus 7 corresponding to a significance of 4.9 sigma for a normal distribution one-sided. So effectively saying that the probability of this being a coincidence is 1 in 10 to the power of 7. That's the level of certainty on this. In the other paper, with a statistical significance, they reproduce it, but with a statistical significance of 5.7 sigma, so even higher in the reproduction of this work. The cat-wise, so we'll go through the discussion. The cat-wise quasar sample exhibits an anomalous dipole orientated similarly to the CMB dipole, but over twice as large, whereas a clustering dipole is also expected from correlations in the spatial distribution of the source. Within the concordance model, the Landau-CDM model, this can be estimated from the distribution of these sources in redshift and the expected matter-power spectrum. It is smaller than the dipole we observe in these higher redshift quasars by a factor of about 65. It is smaller than the dipole we observed in the unique statistical power of our study has allowed us to confirm the anomalously large matter dipole suggested in previous works which use objects selected at different wavelength radio using surveys completely independent of WISE, namely NVS, WNS, SUMS, and TGSS. So I presume other astrophysical, astronomical surveys and observations. The ecliptic scanning pattern of WISE has no relationship with the CMB dipole, so there is no reason to suspect that the dipole we measure, the cat-wise quasar sample, is an artifact of the survey. After L.S. Baldwin, 1984, proposed this important observational test of the cosmological principle, agreement was initially claimed between the dipole anisotropy of the CMB and that of radio sources. So that's why the Doppler shift explanation has sort of been held, has been agreed upon for a good number of years, but looking further out into the galaxy, looking at with a much larger data set, then this doesn't seem to be the case. The two are not matching up, as in the previous sources. If the rest frame of distant quasars is indeed that of the CMB, it would support the consensus that there exists a cosmological standard of rest related to quantities measured in our heliocentric frame via a local special relativistic boost. So effectively, it would be trying to adjust our speed, adjust the speed of the solar system and the speed of our galaxy, such that this dipole is removed and all this becomes one uniform isotropic color. That's what the cosmological principle is expecting. Well, that's not the case as a finding. So, if the rest frame of distant quasars is indeed that of the CMB, it would support the consensus that there exists a cosmological standard of rest related to quantities measured in our heliocentric frame via a local special relativistic boost. This underpins modern cosmology. For example, the observed redshifts of type 1a supernovae are routinely transformed to the CMB frame. From this, it is deduced that the Hubble expansion rate is accelerating isotropically, indicating dominance of a cosmological constant. I've got a few things to say about that, but I'll leave them but another time. And this has led to today's concordance lambda CDM model. If the purely kinematic interpretation of the CMB dipole that underpins the above procedure is in fact suspect, then so are the important conclusions that follow from adopting it. In fact, as observed in our heliocentric frame, the infrared acceleration is essentially a dipole aligned approximately with the local bulk of galaxies and towards the CMB dipole, so cannot be due to a cosmological constant. If it is established that the distribution of distant matter in the large-scale universe does not share the same reference frame as the CMB, then it will become imperative to ask whether the differential expansion of space produced by nearby nonlinear structures of voids, walls, and filaments can indeed be reduced to just a local boost. Alternatively, the CMB dipole may need to be interpreted in terms of new physics, e.g., as a remnant of the pre-inflationary universe. Gordon noted that this issue is closely related to the bulk flow observed in the local universe. Gordon noted that this issue is closely related to the bulk flow observed in the local universe, which in fact extends out much further than is expected in accordance with the lambda CDM model. Or as I would put it, essays, computation, lol. Everything in our universe is essentially moving all at the same speed in one general direction, in that direction, away from the Eridanus supervoid. The bulk of the universe is going like that. That is what's happening. Further work is needed to clarify these important issues. Well, I'm glad I did the work for them. As Ellis and Baldwin emphasized, a serious disagreement between the standards of rest defined by distant quasars and the CMB may require abandoning the standard FLWR cosmology itself. Yes, it should be Gödel, the Gödel metric, which accounts for rotation. Let me just bring up Gödel metric. So this accounts for, it's like the FLWR metric, but accounts for the universe in rotation. And it was done by the one and only famous Gödel. The importance of the test we have carried out can thus not be overstated. So the amplitude of the dipole D, solid vertical line in the cat-wise quasar group versus the expectation assuming the kinematic interpretation of the CMB dipole. The distributions of DSIM from simulations section 3.2 is shown along with its median value dash vertical line. So essentially, what they're saying is that if the CMB dipole, the relativistic, this kinematic interpretation of the CMB dipole was correct, then we would expect the quasar groups dipole to also match up with this one, but the dipole is actually down. That's why the quasar group is dipole is down here. So the two are not matching up, and thus the kinematic interpretation of the CMB dipole, which is the thing that's being tested, is failing. Because if the two were to be expected, then this red line here should be over here. It shouldn't be way out here with a normal distribution of 4.9 sigma, meaning the likelihood of this being a coincidence being 5 times 10 to the power minus 7. That's likely 1 to 5 times 10 to the minus 7. So that effectively is what that paper is showing. It's testing this kinematic dipole interpretation using quasars, and it's not matching up. This paper here effectively reproduces it, but this time with the even greater precision of 5.7 sigma. So if we look at there's no distribution for what they're actually seeing versus what various models are producing or different variations of the kinematic interpretation model of the CMB dipole. So I think we'll leave it there for today, and catch you next time in the Big Bang Kilonova Hypothesis. Hope to see you there. Catch you next time.